Okay, well, let's keep going with these data topics, and we're going to cover 12.4. The I can statement is I can understand and make histograms, histograms, and box plots, All right. Now we're going to start off with a warm-up question, and it just says find the five-number summary for the following data set. So let's run through and take a look. First of all, we notice that they are not in order. That's kind of a pain, but we can deal with that. Let's go through and take a look at what would come first here. I think the smallest number here is 6.7, so I'm going to cross that off and write a 6.7 right there. And again, kind of keeping these underneath the ones that are above there will make it so we kind of keep track of how many there are and we don't lose any of them. Let's see, I think we've got 7.6 next. 7.6. I think 7.8 would come next. And then let's see, we've got an 8.1 and an 8.4 and an 8.4. So we're going to do an 8.1, an 8.4, and an 8.4. We got those taken care of. Next up, we've got a 9.4 here and a 9.4 here. So 9.4 and 9.4. And then we've got that 10, and we finish it off with the 12.6. And again, we see that everything lines up, so we've got the right number here. Now I'm going to just do this as quickly as I can, since this is a fairly small data set. You'll notice that we have 10 of these all together, so that means that the median is right in the middle. So there's going to be 5 on this side and 5 on this side. So I'm going to draw a line right here and write median. It's right in between here, so that's going to be 8.4 for the median. Okay, and then that divides this into a bottom half and a top half. So in the bottom half, we've got these 5 numbers. So again, the middle, so if we kind of go from here and here and here and here, that means the middle one right here would be 7.8. So that's going to be Q1. We'll do the same thing here as we kind of count toward the middle. There's 2 over here and 2 over here, so the middle one right there of that upper half, that's going to be Q3. And of course, the easiest ones to find are the min, that's going to be right here, and the max, that's going to be right here. Now, if we go through, let's say we circled this one right here and we circled that one right there. This is still included in that bottom half. That's one reason why I did that last. So we've got 5 data points. The middle one would be right in the center. It would be the third one. Remember that whole thing, if we did 5 plus 1 divided by 2, that would be 3. So that's going to be the third one in here and the third one in there. Again, lots of different ways to keep track of those, but there's our 5-number summary. So we've got a min, and we've got a max, we've got a median, whoops, get that written right, median, and then we've got Q1 and we've got Q3. So the min is 6.7, the max is 12.6, the median right in the middle of 8.4 and 8.4, so that is 8.4, and then we've got 7.8 for Q1 and 9.4 for Q3. So we've got that all set up. Again, we could talk about the range, so we could find the difference between the max and the min, and we could talk about the interquartile range, but it didn't ask for that, so we'll just leave that the way it is. Now, let's say that the numbers up above represented the mile run times for 10 randomly chosen 7th grade boys, and we'll analyze by doing the following. So find the mean, median, and the mode. Okay, so the median, we've already got that taken care of. So that's going to be 8.4 minutes. Okay, so we've got the median taken care of. The mode also is pretty easy because we look through here and we notice that, well, there's an 8.4 that occurs twice and a 9.4 that occurs twice. So the median, it's going to be, we call this bimodal. There are 2 modes. 8.4 and 9.4 minutes. Okay, so we've got that taken care of, and then we've got to find the mean. And for the mean, we've got to add all of these up. So I'm going to add all those up really quickly and divide by 10. So let's see what we get here. And you can fast forward if you want. So you'll notice I've gone ahead and added all those together. I got 88.4 divided by 10, we get 8.84, so 88.4 divided by 8.4. So we're going to go to the nearest tenth like everything else on here. So we just call that 8.8 minutes. Okay. So we've got the mean 8.8 minutes, we've got the median 8.4 minutes, and we've got the mode. It's actually bimodal. There are two modes, 8.4 and 9.4. All right, then it says we're going to make a dot plot or a histogram to display the data. Now I'm going to go ahead and make a dot plot right now. So let's put, let's see, 6.7. So I'm going to put anything that falls in between 6 and 7 right here. So we've got 1 here, okay. We've got 2 in the 7-minute category. So I'm going to do this. So this would be 6, and this would be 7, and this would be 8. So this would be anything 7 up to 7.999 minutes. We've got 1, 2, 3 in the 8-minute category. And again, notice how I'm making those roughly the same size there. We've got 2 in the 9-minute category. And let's see, we've got 1 in the 10-minute category and 1 in the 12-minute category. So nothing in this 11-minute category right here. So we'll do it like that. Now it says, notice it says make a dot plot or a histogram. So I made a dot plot. I did the X's rather than the dots, but no problem with that. Or it says histogram. So this is where we want to start talking about a histogram. You may have heard of a histogram before. A lot of people think that a histogram is exactly like a bar graph, but there is a difference. Okay. On a histogram, the width of the bars makes a difference, and how far apart they are make a difference. On a bar graph, maybe we'll look at one in a few minutes, but here's a histogram. So basically what we do is we draw a rectangle, and the height of that rectangle represents how many there are in each one of those categories. So if I came over here to this axis right here, let's draw on this vertical axis, we'd mark this off as 1, this is 2, and this is 3, and this is 4. So we know that as we make those, as we make those rectangles, the width of them represents, 1 unit in width, and then the height represents how many of them fall in that category. So this is the 6 to 7 category. There's only 1 in that. This is the 7 to 8 category. There's only 2 in that. This is the 8 to 9 category. There are 3 in that, represented by this taller rectangle. And then in the 9-minute category there's 2, in the 10-minute category there's 1, there aren't any in the 11-minute category, and there's 1 in the 12-minute category. And this is what I mean by on a histogram, the width of the bars makes a difference. So each one of these width, they're basically 1 minute wide, and then again the height tells us how many there are in that category. So the fact that there's a space between the two of these means something when we look at this. It means that there are no zeros, or sorry, no 11s. Nobody did an 11-minute runtime. Now, if we were doing a bar graph, let me show you what we're talking about there. If I did a bar graph and something like this, and we were keeping track of, let's say, red, blue, and green M&Ms or something like that, the width of these bars doesn't make any difference. The fact that it's red doesn't have anything to do with how wide it is. We could make it this wide if we wanted, and then the same thing with all of these others. It would be the height that we would really be worried about. In fact, we could make them any width we want and it wouldn't make any difference. It's really the height that we're concerned with when we do a bar graph. So sometimes these are called categorical variables. We name them, and these right here, these are numeric variables or numeric values here. So this would be more of a bar graph. This is more of a histogram. Again, the width of each one of those makes a difference. Okay, now let's talk about how we make a box plot. We make a box plot using the 5-number summary, and it's also called, or also known as, a box and whisker plot, a box and whisker plot. And you'll see why it's called a box and whisker plot in just a second, but I'm going to run through the steps here, and I'm going to show these values that we came up with here. So here's what we do to make a box plot. We draw short vertical lines above, get this, Q1, the median, and Q3. So above Q1, which is 7.8, so here's 6, 7, 7.8 would be about right there. We're going to draw short vertical lines, about that long. The median is 8.4, so that's about right there. And Q3 is 9.4, so that's about right there. So we draw short vertical lines around there. And then it says enclose these vertical lines in a box. So we're going to put a box around that. So we're basically going to draw these lines right here. So this is Q1, this is the median, this is Q3, and we make a box out of those. Then we draw a line from Q1 to the min. So we're going to put the min on here. The minimum is 6.7. So 6.7 is about right there. We draw a short vertical line and we draw a line to that one. And then we draw a line from Q3 to, you guessed it, it would be the max. And the max on this one is 12.6. So 12.6 is about right there. And we'll draw a line like that. Okay? Now, this is a box and whisker plot. So this is the box, and then those are kind of like the whiskers. I'm not a huge fan of that name. We just call those box plots. There is something called a modified box plot, and it gives us a way to figure out whether or not we've got outliers. And outliers are things that don't really fit the general pattern. So you'll notice we've got this nice little clustered pattern right in here. This 112, that's a little bit off from the center, but not too much. If we had one way out here, like if we had somebody run the mile in like 20 minutes or something like that, that might be what we call an outlier because it doesn't really fit the pattern of the data, okay? So that's how we make a histogram. You can basically think of it as having a dot plot that we put rectangles around, and a box plot is made using the 5-number summary. So we take these 3 middle parts, the Q1, the median, and Q3, we put a box around those, and then the minimum is that bottom line, and then the maximum is that top line right there. And basically it's a way of visualizing each quarter of the data, because remember, from the min to Q1, that's the first 25% of the data, the first quarter of the data. From Q1 to the median, that's the second quarter of the data, third quarter of the data, and fourth quarter of the data. And it's a way to kind of visually tell how spread out things are. You can kind of see that these are this 25%, this 25%, and this 25%. They're all about equally spread out. But if you take a look at this last one, this last 25% is really spread out quite a bit. Okay, and it gives us some visual way to talk about and observe what the spread would be for data. So let's take a look at example number 2. These are the mile run times for 10 randomly selected girls. And so here's what we're going to do. And notice something about this. It's already in order. So let's go ahead and find the mean, the median, and the mode. I'm going to do the same thing that I did before. I'm going to go ahead and add these up. Okay, you can see that I added those up. I got 104.7 divided by 10. So we're going to go to the nearest tenth. So we're going to call this 10.5. So that means the mean is 10.5 minutes for the mean. The median will go to the very middle. So remember, there are 10 altogether. So we're going to go 1, 2, 3, 4, 5. The median would be right here. So right in between 10.9 and 11.1 would be 11. Okay, so there's our median right there. So the median is 11 minutes. And then the mode, the most frequently occurring, is going to be 11.1 minutes. Okay. All right. We need to make a dot plot or a histogram. Let's go ahead and make a histogram. We'll do the same thing we did a second ago. We're going to do, let's see, we've got 1 in the 7-minute category. So this is 5 to 6, 6 to 7, 7 to 8. So we've got 1 right here. So I'm going to make this box 1 unit tall. So I better come over here and kind of give a scale here. So this is going to be 1. This is going to be 2, and we're basically marking off what the frequencies would be here. So in the 7-minute category, we've got 1. In the 8-minute category, we've got 2 girls that ran the mile in 8 minutes something. And let's see, only 1 in the 9-minute category, 1 in the 10-minute category, 3 in the 11-minute category. So again, we make a box that's as high as that mark of 3 there. And then 1 in the 12-minute category, and then 1 in the 13-minute category. So that's about what that looks like. And again, we made a histogram on this one rather than a dot plot. Now we need a box plot for C. So let's take a look here. Remember, the box plot uses the 5-number summary. So we've got the min right here. We've got the max right here. So again, we want the median of that lower half. That's going to be this one right here. That's going to be Q1. And we want the median of the top half. That's going to be Q3 right here. So we're going to put these 3 middle ones in a box. So we're going to do 8.8. So that's about right there, just short of 9. We're going to do 11, so that's about right there. And we're going to do 11.5, so that's only about right there. So we'll put those in a box. And then we'll do the minimum is 7.8, so 7.8 would be about right there. So we'll do a little vertical line here and then extend a short one there. And then we've got 13.3, so let's see, 11, 12, 13, 13.3, about right there. So we'll draw a little line there. Now, again, this is kind of a way to look at this and visually see how the data is spread out. Remember, each one of these represents a fourth of the data. So there's the first quarter, there's the second quarter, there's the third quarter, and there's the fourth quarter. So you can kind of see which of those quarters is the most spread out. If you take a look here, this second quarter is really spread out. This third one's kind of tightly packed together. That one not so much, and then this one's kind of spread out also, but you can kind of visually see how spread out they are because again each one of those represents a quarter. Now I'm going to make this a little bit smaller and then we're going to take a look at this and we're going to ask some questions. So first one is, do you have any questions about how the data was gathered? Now this says randomly selected 7th grade girls, and this says run times for randomly chosen 7th grade boys. So the fact that it says random, that's a good thing. We chose 10 of them to be in our sample. But you might ask, well, how were they chosen? How were they randomly chosen? Did somebody flip a coin? Did they use a random number generator? Did they choose what class they were in, or did they just pick whatever class was convenient? Gym was third period, so they went down third period or something like that. So you might have some questions about that. And basically what I did is I got all the run times for all the 7th grade boys and girls from the gym teachers, and then I randomly selected those with a random number generator. So they were all from this school, so that really is a good sampling for the students at this school. 10, you might argue, we might do a little bit better than 10, but that keeps the data manageable. It took long enough to put these charts together in example 1 and example 2, just with 10 pieces of data each. But that's how we did that, okay? So they're probably pretty good samples. The next question is, what do you notice about the box plots for the boys and the girls? So let's look at the box plots. So here's the box plot for the girls, and here's the box plot for the boys. Now I did these right on top of each other for a reason. So you'll notice that these are scaled exactly the same. I used the same graph on this one as I did on this one. So one thing that you should notice right away, whether you're looking at the box plot or whether you're looking at the histogram, is that the boxes, this entire distribution we call it, is more to the left. In other words, it looks like the boys ran faster. And then if we look at the data, the actual statistics that come from these samples, 8.8 minutes for an average, a mean time versus 10.5, 8.4 for a median time versus 11, and then 8.4 and 9.4 as modes as opposed to 11 minutes for a mode for the girls. So it looks like the boys do run faster, okay? So we're going to write down boys run faster. Now, I'm going to add this just to kind of appease some people. It appears that boys run faster. Now, does that mean all boys run faster? I'm going to write that down. All boys faster. So if you take a look here, there are definitely some girls that ran faster than some of the boys. Okay, so we're not just saying all boys run faster, we're just saying kind of typically boys run faster than girls. Okay, and like it or not, that's generally speaking the way it is. Okay, so what could we say about the mile run time of a randomly chosen boy or a randomly chosen girl? Now, it doesn't say from these particular samples. It says just from any of these from the population from which they were chosen. So I already told you, these are students at our school. So if you randomly chose a boy at this school, a 7th grade boy at this school, and randomly chose a 7th grade girl at this school, we could probably infer, or we could make a guess, that the boy's probably going to run it in about, and I'm going to do this, about 8.4 minutes. And a girl's probably going to run it in about 10.5 minutes, because typically that's what happens. On average, That's what happens. That's roughly what the center of those distributions is, or distributions are. Okay. Now, how big are the samples? The samples are only 10. Do you think some error in our estimates, do you think there is some error in our estimates versus the real average run times? Well, the answer to that is, yeah, there probably is some error there. Not that we did anything wrong, but if we just choose 10 people, it's not going to be perfectly representative. So do you think there's some error? Yes, comma, but it's pretty close. Now, what could we do to improve that? Well, we could probably increase this right here. We could probably go from maybe a sample size of 10 to maybe a sample size of 50 or 60 or something like that. That would probably give us a more accurate estimate, and maybe reduce our error. But again, we talked about why we did 10. Just makes it a little bit easier to deal with. So that's how we take data and come up with some displays like a histogram or a box plot. The next thing we're going to do when we flip it over is we're going to look at some of these. I mean, there are times where you'll just be given a box plot or some sort of display, and you're going to be asked to answer some information about it. So let's take a look at example 3. It says the accompanying box plots can be used to compare annual incomes of 3 professions. So we've got nuclear engineers, police officers, and musicians. We've got a box plot for each one of them. So remember, this means a quarter of the nuclear engineers make this much money. So that looks about, say 50,000 a year to 60,000 a year, somewhere in that neighborhood. The next highest quarter is going to be about 60 to 70,000. The next quarter is a pretty big spread from 70,000 maybe up to about 95,000 or so. And then that highest quarter, the really high paid ones, maybe about 95,000 to about 120,000. And we can look at each one of these box plots the same way. Smallest quarter, second smallest quarter, third, and then fourth. And then same thing for musicians. So let's take a quick look here and let's see if we can come up with some answers to these. And it says, which statement is true? The median income for nuclear engineers is greater than the income of all musicians. So the median income, so you've got to know where to find that, the median income for nuclear engineers. Well, nuclear engineers are up here. This is the box plot. And remember, the middle of the box, that's the median. So let's follow it down here. That's about $70,000 a year. And it says that median income is greater than the income of all musicians. Well, if you come down here, it certainly isn't, because there are some musicians that made a heck of a lot of money. So that one definitely is not true. That one is false. The income for police officers and musicians is the same. The median income for police officers and musicians is the same. Median income is the center of the box. Median income is the center of the box. So that one is true. So this one is the true statement. So we're going to grab that one. But let's just check the other ones. They better be false. All nuclear engineers earn more than all police officers. All nuclear engineers, all of these, earn more than all of those. And the answer to that is no, because we've got this little bit of overlap. We've got these lower paid, maybe entry-level nuclear engineers that don't make quite as much as veteran police officers who've been on the force for a long time. So that one's false also. A musician will eventually earn more than a police officer. A musician will eventually earn more than a police officer. Now that one might be kind of a tricky question that involves a little bit of background knowledge. Does this mean that if you're a musician, you start out here and by the time you're done with your career, you end up here, and then the same thing for police officers? Like a police officer could never make more than this, and a musician will always go from this end to this end? It doesn't, okay? There are people that, depending on what they play or where they live or different things like that, maybe they're always going to be stuck in this category right there. They're never going to make this kind of money unless they maybe hit the big time or go to New York or Los Angeles or something like that. So this is the only one that's true, and we can just look at the graphs and kind of figure out that information. Okay, these are a couple of problems from assignment 12.4b. We're going to do 2 worksheets on this one, and some of them are going to be building box plots and histograms, and others are just going to be interpreting. So let's take a look at this one right here. The accompanying box and whisker plot represents the scores earned on a math test. First of all, it says, what is the median score? Again, you've just got to be able to look at it and know that is the middle of the box, so that's going to be 75. What score represents the first quartile? Which one is Q1? Again, the top of the first quarter. There's the first quarter right there, so it's going to be 70. Which statement is not true? So all of these are true except for one. So 75 represents the mean score. 75 represents the mean score. Now think about that for just a second. Does 75 represent the mean score? That means add them all up and divide them how many there are? That one is not true. That one's not true. If this said median, then it would be okay. So let's make sure that the rest of these are false. 85 represents the third quartile. There's Q3, 85. 100 represents the maximum score. Yep, the max would be the very end of that whisker there. 55 represents the minimum score. Yep, we're in good shape there. And then this last one, a score of 85 on the box and whisker plot shown refers to, so let's look at 85. It refers to, kind of like what we pointed out right here, it refers to the third quartile. So it's that answer right there. It's not the median is right there. It's not the max is right there. And then this is a good question. Can you find the mean just by looking at a box plot? Good question. Can't find. We would really need more information than just a box plot in order to figure that out. So these are pretty cool displays. There are other ways of looking at data other than some of the ways that we've already looked at, but these are really good, so get used to histograms and box plots.